Okay. Apologies. All right. So we'll work through the practice final exam. I hope you guys had a chance to work through this, but we'll go through. Okay. So numbers 1 through 4 says we're going to check to see if these conditions are met. Do you guys remember all of this stuff? Okay. Okay, so number 1 says a study is performed to understand the relationship between bright lights and headaches. 80 randomly selected subjects are exposed to bright lights, 20 complain they experience headaches, 90 randomly selected subjects are exposed to less bright lights, and 12 complain about headaches. Are any conditions violated? Okay, and so there's 3 conditions that we need to check: the independent and random assumptions, the big population condition, and the large sample condition. Okay, so is the independent and random assumption, is that met for number 1?
Yes.
Yes, it says we've selected 80 here randomly and 90 here at random, so this condition is met. Is that okay? What about the big population condition? Okay, so here we are looking at 80 subjects here and 90 subjects here. Who would our relevant population be? Okay, so these are samples, right? These 80 people that we selected, this is a sample, and the 90 people we selected are a sample. So the relevant population would be anybody who might be exposed to lights and might experience a headache, okay? So that's pretty much everybody in the world, okay? So the question now is, is the relevant population bigger than 900 or 800? And the answer to that is yes, right? So the big population condition is also met. Is that okay? I'm not writing anything down, but I'm just kind of talking these through. And the last one is the large sample condition. Okay, large sample condition means we need what? 10%. No, the big population is you cannot sample more than 10%. Smaller than 10%. The large sample condition means for large sample, you need 10 success and 10 failures. And 10 failures, okay? And if you don't have successes and failures counted out directly, you need n times p to be greater than or equal to 10, and n times 1 minus p to be greater than or equal to 10, okay? So this is problem number 1, checking the large sample condition. So in this problem, how many successes do I have? So here we have 2 samples, so we have 2 sets of successes. We've got, it seems a little odd, but we're going to say if they experienced a headache, that's quote-unquote success. So 20 is bigger than 10. So if 20 out of 80 had headaches, how many did not have headaches? 60, right? So 20 have headaches, and this is no headache. Okay, both of these numbers are bigger than 10. So that's okay. What about the other side? We have 12 headaches out of 90, which means 78 had no headaches. Okay, so both of these are also bigger than 10. So the large sample condition is met. Okay, so the answer to number 1 is D, no conditions are violated. Is that okay with everybody? Any questions on number 1? Okay, a researcher wants to make a confidence interval for how common a certain disease is. He finds 300 randomly selected subjects and 2% have the disease. Are any conditions violated? Okay. Is the independent and random assumption condition met?
Yes.
Okay. He says we've selected 300 people at random, so that condition is met. Okay. What would the relevant population be? We want to know what percentage of the population have the disease. So the population is everybody, okay? Like everybody in the world. So is 300 more than 10% of everybody in the world? No, far from it. And so, so the big population condition is not violated, okay? And lastly, let's check the large sample condition. We want to make sure we have at least 10 successes and 10 failures. So that means what? N times P and N times 1 minus P have to be bigger than 10, because we're not given the count. So we check N times P, and what do we have? We have 300 times 0.02, and that gives me 6. This is not bigger than 10. Okay, so as soon as one of these things is smaller than 10, we can stop. So this means large sample condition violated.
So there could only be one condition that gets violated? Not multiple?
Technically, multiple conditions could be violated. I'm going to try to write the test in such a way that only one condition is violated per problem, okay? Just to keep things clear. Student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets, finds data from 100 people and finds that 45 of them answered yes to his questions. Are any conditions violated here? Okay, so we see that it's the sample is not independent, not an independent and random sample. So he's not selecting people at random. Now, it doesn't say anything about the size of the school, okay? So if the school were smaller than 1,000 people, we might be violating the big population condition. So that's a little ambiguous, but clearly one condition that is violated is the not independent and random sample condition. And lastly, number 4, company wants to survey its employees. It has 800 employees total. It decides to select 100 of the employees randomly and interviews each of them. Are any conditions violated here? The big population, because our population is 800 and our sample is 100. That's more than 10% of our population. So big population condition violated. Okay. Any questions so far on numbers 1 through 4? Okay, so you'll see a handful, probably around 4 or 5 questions on the final, just like this. Of course, different though.
So number 4 is which letter is correct?
So number 4 would be B, big population condition. Number 3 is A, violates the random and independent randomization assumption.
You don't have the answers posted, right?
I don't have the answers posted, no. We're going to go through them here. I have a suspicion that if I post the answers, nobody would come to class today.
True.
Tonight.
Yeah, so so I'm, you know.
Is it gonna be tonight?
Well, so I'll do this video. Huh?
Hey.
Okay.
Are you
So,
doing anything now? Yeah.
I'll post these notes up. Okay.
Is your sister paying you to come?
I know, maybe. All right, let's go through questions 5 through 10. All right. I should have some kind of reward for those who stay to the end. A farm wants to test 2 different diets for their cows to see which diet causes more weight gain. Okay, because they're in the business of fattening their cows. They randomly select 10 cows to give diet 1, and they select 12 cows for diet 2. After 2 weeks on diet 1, the 10 cows gained an average of 15.2 pounds with a standard deviation of 4.1. After 2 weeks on diet 2, the 12 cows gained an average of 12.6 pounds with a standard deviation of 3.4. The following questions refer to a 95% confidence interval for the difference in average weight gain. Okay, so I just want to point out a few things that I've set up in our study guide. And the first thing, on page 1 says the most important thing is whether you are dealing with 1 sample proportions, 2 sample proportions, 1 sample mean, or 2 sample means, okay? And you just have to ask, do I have numeric variables or categorical variables? If it's categorical, it's proportions. If it's numeric, it's means. And do we have 1 sample or 2 samples? So as we read through this problem, how many samples do I have?
2.
I have 2 samples, right? I have 10 cows for sample 1, 12 cows for sample 2. Do I have a numeric variable or a categorical variable? Numeric, right? We're looking at average weight gain. So for this problem, so problems 5 through 10, I've got 2 samples, and we're dealing with means. Okay, it's a numeric variable.
And you said categorical.
So if you have a categorical variable, it will always be proportions. Okay, and if it's a numeric variable, it will always be means. There's no, okay, and if it's proportions, it's always Z table. If it's means, always the T table. Okay. And then, as we read it, it says we're talking about a confidence interval, right? So we have a confidence interval going on. Okay. So in your notes, you should probably have that the confidence interval is x bar 1 minus x bar 2 plus or minus t star times the square root s1 squared over n1 plus s2 squared over n2. Okay. You can also check the study guide, and it says, okay, well, if we're going to do a confidence interval, it kind of breaks it down. It says for 2 sample means, the center of the interval is going to be x bar 1 minus x bar 2. I don't know if you guys can see this. The critical value for the confidence interval when you're dealing with means is going to be t star, and the standard error, 2 sample means, s1 squared over n1 plus s2 squared over n2, square root of that. So let's take a look at our questions. Yes?
I haven't taken a look at it yet, but can we print that out for the
Note sheet?
note sheet?
Yes, if you want to print this out and use it as your note sheet, that's fine. If you want to take like a different colored pen and write some extra notes in the blank areas, that's also allowed. That's fine. Okay. I provide this to help you guys out. It's not. I don't put this on the internet just so you look at it and throw it away or something, you know. So, but you're of course you can make your own note sheet, because you know you might like your own more. Okay, but you can't use this and another note sheet. Okay, because that would be.
Use a backup note.
So well, this is two-sided, but okay. Yes.
Can you use this one and write in that paper a couple of notes?
Yes. Yes. I think that's what I just said. So you can print this out. No problem. You can print this out, and then there's white space here, so you can write notes to yourself. Say like, you can do it.
That's a motivation.
Yeah.
Don't let anyone put it in.
Yeah. Don't let anyone ever dull your sparkle. So I remember seeing someone's note card that said, breathe, take your time, don't make silly mistakes. And I thought, oh, that's pretty good, right? Because the student's problem was rushing through things and making silly mistakes. So,
That's a good.
so don't, yes.
So it's not gonna be like 2 pages to final, it's gonna be how many questions?
The final exam probably going to be like 50
So
questions.
there's duplicates of each problem, or
I don't know what you mean by duplicate. There's
because this is a two-sided study guide, right?
the study guide has only 2 pages, but the practice final is like 6 pages long. So
Okay, and this encompasses the material, right? There's not going to be like extra material from what we learned here.
I'm not going to put any questions on the test that I did not teach in class. I don't wait. Sorry, what?
We learned a lot of new material this part after the midterm. So
Yes.
are we gonna, is this all the material or?
So I think the practice final is pretty thorough.
Okay,
Um,
that's the question.
okay.
Yeah, you just-
Okay. All right. So let's tackle this. 95% confidence interval. What's the center of the interval? It's going to be x bar 1 minus x bar 2. Okay. This we can see from our formula for the confidence interval, or if we weren't sure, we can go to the study guide and it says, what's the center? The center is this. Okay. So as we read the problem, we should go through and we should identify all of the different things here. Okay. And so we see 10 cows. What's that? That's going to be N1. 12 cows is N2. 15.2 pounds, that's X bar 1. And 4.1, that's going to be S1. 12.6 is X bar 2. And 3.4 is S2. So I always recommend going through a problem, either circling the numbers and indicating what they are, or in your notes, kind of creating a listing of the different values that you'll need to use. That way you're not going to get things mixed up. Because even if I don't write everything down, sometimes I get them mixed up if I just try to keep track of everything in my head also. Okay, so the center of the interval, we're going to do x bar 1 minus x bar 2, so I'm going to do 15.2 minus 12.6. And I get a difference of 2.6, and that's going to be the center of my interval. For a 95% confidence interval, what will we use for T star? So T star comes from the T table, and it says we have a 95% confidence interval, and my degrees of freedom is equal to n minus 1. But I use the smaller n, right? So I've got n1 is 10 and n2 is 12. So I'm going to do 10 minus 1, and so my degrees of freedom is 9. I've got 9 degrees of freedom. So we're going to go to our table. We're going to look up 9 degrees of freedom, 95% confidence. My T star is 2.262. Okay. As I'm going through this, if you guys have any questions, raise your hand or say, hey, explain that to me, okay? Yes?
And the rule for the DF line was to choose the least.
Yes, so I have 2 n's here, right? I got a 10 and I have a 12, so I'm going to use the 10, okay? So degrees of freedom, we always want to kind of say we've got less degrees of freedom than just to be safe, okay? It's always better to have less, okay? It's like inviting people to a party. You always want to invite fewer people than what you have food for or something, you know? Or I don't know. I guess if you want to make sure everybody gets a meal. What am I doing? Okay, so number 7, what's the value of the standard error? Okay, so the standard error is this thing. Again, you can always check the study guide for 2 sample means. Standard error is S1 squared over N1, S2 squared over N2, square root of that, okay? So I'm going to just plug in values from our thing. So S1, looking at this, is 4.1, and N1 is 10, okay? And let's look at S2 and N2. S2 is 3.4 and N2 is 12. So I'm going to have 3.4 squared over 12. It's a matter of punching this into a calculator now. 4.1 squared divided by 10 plus 3.4 squared divided by 12. So I'm just punching that in straight into my calculator. I get this number, and I'm going to take the square root of that. Square root of 2.644333, etc. I punch that, and I get 1.626. 1.62614, etc., etc. Yes?
Yeah, in the textbook it would talk about like you punch it in and there's like the whatever statistics setting or something, and it gives you all these different answers.
That is true. If you have so if we went to a public high school or something where the school has a budget to buy fancy calculators for everybody, we could do that. I didn't want to make it a requirement that every student needed to buy a $100 calculator, so I'm kind of teaching you how to do it with a $20 calculator, $15 calculator.
But so you can.
There is,
if you have that option.
if you have a fancy calculator, you can punch everything in there, and it will spit it out. But that's like another, you have to be taught and trained on how to use the calculator, and I mean, we're not going to do that, so. Okay.
So on the actual final itself, there will be multiple choice answers to determine.
Yes, there will be multiple choice answers, just like our quizzes and stuff. Okay. So on this one there wasn't, but on the final there will be.
Okay.
Okay, so we're going to make a 95% confidence interval for the average weight gain. So we're going to do 2.6 plus or minus 2.262 times 1.62614. So I have 2.6 plus this. I'm going to multiply this by 2.262. So I get 2.6 plus 3.678, and I get 2.6 minus 3.678. Oops.
How similar is the final to this practical final?
In my opinion, very similar,
Exactly.
but of course it's not going to be exactly the same. It's hard to answer these types of questions.
Is there anything that's not on the practice final that is on the final?
Okay, so all of the questions on the final are different from the questions on the practice final. Okay, I'll just tell you that. But they are similar. Okay, they're coming. I'm the one writing this, right? So they're coming from my brain, and I'm trying to make the practice final representative of the actual final. Have the practice quizzes that I've posted been representative of the actual quizzes? In my opinion, yes. So, in my opinion, the same applies to the final.
Wonderful.
But, I always get whiners and haters every quarter, so I can't make everybody happy unless I just give everybody A's, and I'm not going to do that. Based on your 95% confidence interval, do you conclude that there's a difference in the average weight gain? So our confidence interval goes from negative 1.078 to 6.278. How do we decide if there's a difference in the average weight gain between the two populations? I'm looking to see if 0 is between the ends of the interval, right?
Yeah.
So is 0 within our interval?
Yes.
Yes, so 0 is within our interval. So what does that mean? Do I have evidence that there is a difference between the two, or do I not have evidence? Yeah, so I say I do not have evidence that there is a difference between the mean weights.
Can we reach that conclusion solely because there's a zero conflict?
Because 0 is between -1 and 6.278.
So that's how we reach that conclusion?
That's how we reach our conclusion when doing a confidence interval for a difference between two means. Also, two proportions, the same idea holds there also. Okay?
What is that actually mean?
What is weights? WTS for as an abbreviation for weight. There we go. And number 10. If I made a 90% confidence interval, how would it compare to our 95% confidence interval? Okay. So with a 90% confidence interval, the only thing that would change is this number for T star. And it would become smaller. Okay, I can go to the table and I would see that rather than using 2.262, I would use 1.833. Okay, so everything else would stay the same, except this would get smaller. So that means this number gets smaller. So our 90% confidence interval would be more narrow. Than the 95% confidence interval. Okay, good? Good.
So, I have a question.
Okay.
For number 10,
Yes.
the multiple choice available answers would be like.
It would probably just be a bunch of nonsense answers and this correct answer. So it might be like our 90% confidence interval would be more narrow than the 95. Our 90% confidence interval would be wider than the 95. Our 90% confidence interval would be the same, or we won't know unless, you can't tell without more information. I don't know. I would probably just make up a bunch of other stuff that sounds kind of maybe reasonable to a person who doesn't know, but you would know that this is the only correct answer. Okay. We'll keep going here. Okay, we're going to the ruler and yardstick factory. I always wanted to go there. The yardsticks it produces are supposed to be 3 feet long. You measure a random sample of 40 yardsticks and find that the average length is 3.02 feet. Oh my goodness. And with a standard deviation of 0.03 feet. So those, for our international friends in America, we talk about yards. 3 feet, it's like a meter, but it's a little bit less. This is how we play football. American football, that is. So is this evidence that the machine is producing yardsticks that are too long? So we're going to do a hypothesis test. Of course, the most important thing for any of these things is, do we have one sample or two samples? Are we dealing with means or proportions? So how many samples can we see identified in this problem? Just one, right? One sample of 40 yardsticks. So I've got one sample. And then, am I dealing with means or proportions? So do I have a numeric variable or a categorical variable? Yeah, so we see a few words like average length. So that should be an indicator to us that it's a numeric variable, okay? Average is like another word for mean, okay? So we've got a numeric variable, so we're dealing with means. Okay, one sample means, and then it says it's asking stuff about about a hypothesis test, okay? So we have a hypothesis test going on. Okay, so the first thing says, is this a one-sided or a two-sided test? How do we know if it's one-sided or two-sided? Okay, we look at this question. Is this evidence that the machine is producing yardsticks that are too long. Does that seem to indicate? Yeah. So that means we're going to have a greater than or less than sign, greater than sign because we're looking at too long. So this is going to be a one-sided.
Two-sided would be too long or too short?
Yeah. So for number 11, the answer is one-sided. If it said, you know, yardsticks that are different. So if the question said yardsticks that are different from 3 feet, then this would be a two-sided test. Number 12 says, what would our hypotheses be? So we would have a null hypothesis and an alternative hypothesis. Okay? When we're dealing with one sample means, what do our null and alternative hypotheses look like? Okay. Okay. So if you have forgotten, this is when looking at the study guide is helpful. What would your hypotheses be? Okay. So you're looking up, do we have one sample proportion, one sample mean, two sample proportions, two sample means? Okay, we've got, for one sample mean, the null hypothesis is mu equal to 30, and mu not equal to 30, of course, not necessarily 30, and maybe greater than, less than, or equal. So our null hypothesis is mu equal to some number for one sample mean. So we've got mu equal to something, and because it's one-sided, we want to know, is it too long? So it's going to be mu greater than. And we want to know, are the yardsticks too long? How long is the yardstick supposed to be?
3 feet.
Exactly 3 feet. So our null hypothesis is that mu is 3 feet, and our alternative is that our null yardsticks are longer than 3 feet. Okay, so this would be the pair of hypotheses that we would use. Okay, or, you know, in words, it would be yardstick are exactly 3 feet, and yardsticks are longer than 3 feet long. Okay. What is the value of the test statistic? Okay. So the test statistic is, okay, well, I know, but if you don't know, you can always go to the study guide and you can see, okay, so it says it's always in the form of observed minus null divided by the standard error. Okay, so for one sample mean, we're going to use the x bar. And what's in the null is 3, okay? Divided by the standard error. And the standard error for one sample mean is s over the square root of n, okay? So standard error is s over the square root of n. So let's go through our problem and identify x bar, s, and n. Okay? So 3 feet in our problem. Yardsticks that produce 3 feet, what is this? This is the value in the null hypothesis. When you measure a random sample of 40 yardsticks, what's this?
N.
This is n. 3.02, this is x bar. And 0.03, this is
S.
s. Okay, so we can do this. So here, actually, let me just, our generic form of this is x bar minus mu 0 over the standard error, where standard error is s over the square root of n. Okay, so the standard error is going to be 0.03 divided by the square root of 40. So I'm going to do 0.03 divided by the square root of 40. I get 0.00474. Okay, so my test statistic is x bar minus mu 0 divided by the standard error. So my x bar is 3.02 minus the mu in my null hypothesis 3 divided by the standard error 0.00474. So I'm going to punch this into my calculator. I'm going to do parentheses 3.02 minus 3, and then I'm going to hit divide by, and because I already have 0.00474 in my answer, I'm going to just hit divide by the answer. Okay? And here I get 4.21637. So that is my test statistic for number 13. So far, so good? Okay. Whoops. Okay, so now we're going to look up the p-value. Okay? So here I've got to figure out my degrees of freedom. Degrees of freedom is n minus 1, so I'm going to have 40 minus 1, 39 degrees of freedom. And I go to my table for 39 degrees of freedom. And I see I don't have 39 degrees of freedom, so I always have to round down and we're going to use 30 degrees of freedom. Okay? And we're going to see where 4.21637 goes. So with 30 degrees of freedom, the largest number I have is 3.385, and I have 4.216 beyond 3.385. Okay? So 4.216 is greater than that last number, 3.385. So what can I say about my tail area? So I look at the top, 3.385 corresponds to 0.001. So my tail is going to be what compared to 0.001? It's going to be less than that, right? Because the tail area gets smaller as the test statistics get larger. Okay, so we keep that in mind. So because my test statistic is bigger than the last number in that column, my tail is going to be smaller than 0.001. So that means, do I need to double this to get my p-value, or can I just leave it? I leave it, right? Because I look at my alternative hypothesis. I have a one-sided test. So I just, I leave it as is. And so I say my p-value is less than 0.001. So that's number 14. Okay, what about number 15? It asks, if alpha were 0.05, what conclusion do we make? Would we reject or not reject the null hypothesis? So here my p-value is less than 0.001. That means my p-value is indeed also less than alpha, which is 0.05. So that leads me to reject the null hypothesis. And if that was a mistake, what kind of error did we make? If the conclusion we just made was wrong, what kind of mistake? So we chose to reject the null hypothesis. If this was a mistake, what happened? Yeah, we committed a type 1 error if it was a mistake. If rejecting H0 was a mistake. Is that good? You guys need another minute to get this down, or are we good? Okay.
We're gonna post this video online tonight, right?
That's the plan. If, you know, sometimes my computer messes up in the recording. Sometimes it records it at like 3 frames per second or something. I hope that's not the case. All right, I'm going to keep it going. I'm just going to try to power through everything, get you guys out as quickly as possible, and I'll do that. Okay.
I'm going to take a break before that.
We'll see. We'll see how we're feeling. Okay. If you really want to take a break, we can take a break. Okay. Questions 17 through 22. Okay, let's do this. All right. Researchers believe that 14% of the population is left-handed. Local school decides to see if their students have a different proportion of left-handed people. School has a total of 1,500 students, and they randomly select 90 students for the study. They find that 15 of those are left-handed. Is this evidence that the proportion of left-handed students at the school is different from the population proportion? Okay, how many samples do we have, and are we dealing with means or proportions?
One sample.
Okay, we've got one sample. And categorical variable or a numeric variable, means or proportions?
Categorically.
It's categorical, right? So we're dealing with proportions. You know, we're asking, is somebody left-handed or not left-handed? That's going to be a proportion. Okay, one sample proportion. Okay, and it looks like we're making a confidence interval. So as we are reading through this, we're dealing with a confidence interval. Okay, what is the sample proportion? Okay, so let's actually go through and we'll identify certain things, okay? 14%, what is 14%? This is the population proportion P, okay? What is 1,500?
N?
No, this is our school's population, okay? All right. All right, I'm sorry. This is P0 from the, I guess, the nation, I should say. Okay, 90 is the N for my sample. And what is 15? 15 is my X. Okay, so the sample proportion P hat is X over N, so I'm going to do what? 15 over 90. So I do 15 divided by 90 and I get 0.1666. So gotta just round off somewhere. So we'll do that. And 18 says you want to make a 90% confidence interval. What critical value Z star would you use? Okay, so when we are doing a confidence interval for proportion Z, we just have 4 values that we need to memorize, right? Or have on our note sheet, which I have put on your study guide also. What's the critical value for Z star? And I say, okay, 90% confidence interval, 1.645. So our Z star (1.645). Okay, and you know, you might want to just put this somewhere: P hat plus or minus Z star times the standard error, where the standard error is equal to P hat times 1 minus P hat over N. Okay, so let's take a look at number 19.
Yes, sir.
Okay, what's the standard error? Yes, question.
You said that if we don't get a confidence interval, we use 90%. Is that the default value? Did you ever say anything like
Oh, if 95%. So generally, you're going to do 5% or 95%. 5% for alpha if it's not specified, and if the confidence level is not specified, you assume 95%. For some reason, those are the numbers we like to go with.
It'll be indicated.
It'll generally be indicated in the test. Okay, so when making a confidence interval, what's the standard error? Again, if you don't remember, for the standard error, it will say one sample proportion P hat times 1 minus P hat over N. And it's important that we have the hats here, okay? So we're going to have 0.16667 times 1 minus 0.16667 over N, which is 90, and I take the square root of all of this. So I actually have 0.1666 whatever in here. So I'm going to use that as my answer. I'm going to just do answer times parentheses 1 minus the answer, okay, divided by 90. Can you guys see how this would be equivalent to what I've got in the equation? I'm going to go ahead and hit equals, and then I'm going to take the square root of that answer. And I get 0.03928. Okay. So this is my standard error. Number 20 says, okay, what's going to be the center of our interval? Well, that's easy. That's p hat, so that's going to just be 1.1667, okay? And again, you can always consult your study guide, and it says the center is going to be p hat right there. 21 and says, okay.
Sorry, so what was the
Yeah.
difference between 17 and 20? If they're both using p-hat?
The answer numerically is exactly the same. The question is just written differently, right? What's the sample proportion? What's the center of this interval? It's the same thing, right? It's like, who was the 16th president? Abraham Lincoln. Who is the president that led America through the Civil War? Abraham Lincoln, okay? I mean, if you know what you're talking about, you know that's the same question, but it's like different things, okay. Abraham Lincoln. Who's on the penny? Abraham. Okay, all right. Anyway, you know, we'll stop here. Make a 90% confidence interval for the proportion of left-handed students. Okay, so we're going to do p hat plus. All right, I already have that written there, so we'll just plug in our numbers: 0.1667 plus or minus. Z star 1.645 times 0.03928. So let's multiply this by 1.645. So I have 0.1667 plus or minus 0.0646. So I'm going to we'll do this 0.1667 plus 0.0646. So on the high end, I got 0.2313, and on the low end, let's 0.1021. All right, so this is my confidence interval. And so the last question is, does our confidence interval provide evidence that our school's proportion is different from the national average? So our national average is 14%, right? So 14% national proportion. So I'm going to look to see, is 14% within my interval? And the answer is yes. 0.14 is within the interval. So what does that mean? Yeah, we do not have evidence that our school's proportion is different. Number 22, okay. Just let me know when you guys are ready to move on.
Ready.
Ready, okay. Then we will keep going. Tw 23 to 27, Starburst and Jolly Ranchers. There was a time I was eating too much candy, so now I'm eating too much McDonald's, but okay. A bag of Starburst candies contain 80 pieces, and 12 of them are cherry flavored, the best flavor. The bag of Jolly Ranchers contains 70 pieces, and 14 of them are cherry flavored. Assuming that these are truly random assortments, does this provide evidence that Starburst and Jolly Ranchers have a different proportion of cherry flavored candies? This is a very important question. So the Starburst candies, 80 pieces total, 12 of them are cherry. Jolly Ranchers, 70 pieces total, 14 of them are cherry. Okay. All right, what are we dealing with here? We got one sample or two samples? Two samples, okay, Jolly Ranchers and Starburst. And are we dealing with proportions or means? Proportions, right? We want the proportion that's cherry. It's a categorical variable, so we're dealing with proportions. And as we look, it looks like we're performing a hypothesis test. Okay, so, you know, if you do this for every, you know, question on the test, it will help you a lot. Just say, hey, I've got two samples and it's proportions, or two samples and it's mean, or whatever. Set that straight in the beginning. That will help you avoid a lot of pain later on. Okay, so we want to set up our hypotheses. So what is the hypotheses that we use for two samples proportions? Okay. Well, if you're not sure, you can check with the study guide. And here I've got P1 minus P2 equals 0, or we can also just say P1 equal to P2. And the alternative is, are they equal, not equal, greater than, or less than? We want to know, are they different? So we're just going to say not equal. Okay? What's the value of P hat? Okay, so P hat is x1 plus x2 over n1 plus n2. This also shows up in your study guide. Right here, you got to figure out P hat, where you add up the total successes and divide by the total observations. Okay, so success in this case would be the cherry flavored candies. So here we're just going to have to call one of these as sample 1 and sample 2. It's actually labeled group 1 and group 2. So 12 is going to be x1, and 80 is n1, and 70 is going to be n2, and 14 is x2. So I'm going to have 12 plus 14 divided by 80 plus 70. So make sure you do 12 plus 14 and figure out that's 26, and then you do 80 plus 70, and you get 150. Do not do 12 over 80 plus 14 over 70. That's going to be wrong. So we're going to do 26 over 150, and I get 0.1733 for my p hat. Okay. Again, do not do 12 over 80 plus 14 over 70. This is going to give you, 0.15 plus 0.20, which is 0.35. That's wrong. So using that, we're going to find our test statistic, okay? So again, our test statistic is going to be P1 hat minus P2 hat over the standard error, where our standard error is equal, and again, if you forgot this, you can always check here. It's P hat times 1 minus P hat over 1 over n1 plus 1 over n2, entire thing square root, okay? So you're probably going to want to have these formulas written down in your note card, or you can use the study guide, whatever you wish. I'm going to go ahead and do this calculation. I have P hat already in my calculator, so I'm going to just use answer times parentheses 1 minus the answer. That's going to be P hat times 1 minus P hat times parentheses 1 over n1, which we said was 80, plus 1 over n2, which we said was 70. I calculate that, and now I get the square root of all of this, square root of the answer. I get 0.06195. So now I can do P1 hat minus P2 hat, okay? And so P1 hat is going to be 12 over 80, number of cherry flavored Jolly Ranchers divided by the number of Jolly Ranchers in the bag. P2 is going to be cherry flavored Starburst. 14 divided by 70. Okay, so 12 over 80 gives me 0.15, and 14 over 70 gives me 0.20. Or you don't even have to do that. You can do parentheses 12 divided by 80 minus 14 divided by 70, and then I have the standard error in my calculator already, so I'm going to just hit divide by the answer. Okay, make sure you have the numerator in parentheses there. Okay, and you get negative 0.80707 as your test statistic. Negative 0.807. Okay. Yes.
N1 is 80 and N2 is 70.
Yes, N1 is 80 and N2 is 70. So as we're reading through the problems, we circle these numbers. 80 is N1 and 70 is N2. Okay? So our test statistic is negative 0.807. And to get a p-value, I'm going to look this up where? In the z table, right? Okay, and the z table means I have to round off to 2 decimal places to look it up. So we're going to look up negative 0.81 in the z table. Okay, so I go to the reference table. We're going to look up negative 0.81. Negative 0.81, and I get 0.2090. Okay, so we get the area to the left is equal to 0.2090. Is this my p-value? What do I have to do to it? I double it, right? I have a not equal sign, so I've got a two-sided test, so I have to multiply this by 2. So my p-value is equal to 2 times this, so I get 0.4180. This is my p-value, okay? And we know we don't have to do 1 minus this, because if I did do 1 minus this, this would come out to be very close to 0.80, and we know our tail area is always less than 1/2, and if I were to double 0.80, then I would get like 1.6, okay? And we know we can never get a p-value bigger than 1. Okay, so I doubled it and I got 0.4180. That's fine. I leave it at that. My p-value is this. So what is the conclusion that I make based on this p-value? Well, my p-value is bigger than 5%. So that means I do not reject the null hypothesis. Is this good? Is this all right that we're going through the practice final? I can't tell if I'm just boring you all to tears.
So exciting.
Huh?
So exciting.
Well, you know, it's not that I want it to be exciting. I just wanted to make sure that it's useful for you guys.
Yes.
Okay. Okay. If it's useful, I will keep going. Make sure. Okay. Oh shoot! I didn't actually. I made a mistake here. Okay. Well, I'll have to clean that up. Researchers want to know if drinking caffeinated drinks improves reaction time. They randomly select volunteers in a blinded experiment, give some of them caffeinated drinks and others non-caffeinated drinks. Then they record reaction time. 30 people had a drink containing 300 milligrams of caffeine. The average reaction time was 580 milliseconds with a standard deviation of 110. 25 people had a drink containing 0 milligrams of caffeine. The average reaction time was 640 milliseconds with a standard deviation of 130. is this evidence that drinking caffeine improves reaction time? Okay. When performing a one-sided hypothesis test, what should the hypotheses be? Okay, so looking at these, we are looking, we have to decide if we have one sample or two samples. What do we have? Two samples, right? It says group 1 and group 2. Some people had caffeine, some people did not. So I have two samples. Do I have a numeric variable or a categorical variable, or are we dealing with means or proportions? Means, right? We're looking at how much the reaction time. Reaction time measured in milliseconds is a numeric variable, so we are dealing with means, and we're doing a hypothesis test. So what should our hypotheses be for number 28? Okay, two samples means our null hypothesis is going to be what?
P1.
When you're dealing with means, it's never p, it's always mu. Okay, so it's going to be mu1 equal to mu2 versus mu1, and we want to know, does this improve reaction time? So what does it mean to have better reaction time? Okay, so, well, let's think about this, okay? If we say someone has good reaction time, does that mean it takes them longer to respond or less time to respond? Right? They respond more quickly. So that means their reaction time is actually less, right? So the people with caffeine should have a shorter or smaller reaction time to have an improved reaction time. Okay, so we have to, read the problem carefully and think, okay? Improved doesn't necessarily mean greater, okay? Bigger isn't always better. In the case of reaction time, smaller is better, right? We want people to be faster in their response. Okay, observed difference between the means. So what was the let's go through and label our x1 and our s1 and our n1. So 30 is what? This is n1. 300 milligrams of caffeine, is that anything? No, it's not relevant to the question, okay? It's just thrown in there to kind of just check to make sure we know what we're talking about. The reaction time, though, is x bar 1, and 110 is our s1. 25 is N2, 0 milligrams is nothing, 640 is X bar 2, and 130 is S2. Okay, so the observed difference in means, okay, again, in any of these things, if you're not sure, you can always look at the study guide, but this is just X bar 1 minus X bar 2. Okay, what's the difference that we observed between our samples? Okay, so it's going to be 580 minus 640. Okay. And I get negative 60. So those who drank caffeine were 60 milliseconds faster. Okay, what's the resulting test statistic, T statistic? Okay, so let's look. We're going to have X bar 1 minus X bar 2 over the standard error. Our standard error is given by S1 squared over N1 plus S2 squared over N2. So I look at my numbers. I have 110 squared over 30, 130 squared over 25. So oops, 130 squared over 25, and I take the square root of that. So again, it's always helpful to just label all of your numbers in the problem so that when you're plugging them into the formula, there's no fiddling around. So I'm going to do 110 squared divided by 30 plus 130 squared divided by 25 and I'm going to take the square root of this. I get 32.85. So now I have negative 60 divided by 32.85. So negative 60 divided by the answer right there. I get negative 1.826. Okay, so we're going to get the p-value. So we're going to go, we have to look this up in our t-table, right? Okay, so how many degrees of freedoms do I have? 24. I would do n minus 1 using the smaller. I've got n1 is 30 and n2 is 25. So I'm going to do 25 minus 1, 24 degrees of freedom, exactly. So I go to my table, I look up 24 degrees of freedom. So, all right, let's see, 24 degrees of freedom, and I'm looking up 1.826. So I just ignored the negative. So at 24 degrees of freedom, 1.826 is in between these two columns. So I'm in between 0.05 and 0.025. Okay, so my tail is between 0.05 and 0.025. Okay, and so we just look and we go, oh, okay, I gotta put my signs this way. Do I have to double the tail, or do I leave it to get my p-value? I leave it, right? Because I've got a less than sign. So my p-value is also going to be between 0.025 and 0.05. So let's see. Performing a one-sided hypothesis test, what conclusion do we make? If let's say alpha is 0.05, my p-value is less than alpha. We reject the null hypothesis, and that means we have evidence that what? We have evidence that caffeine, that, you know, the caffeine reaction time is faster than the no caffeine reaction time. All right, and if that conclusion was wrong, what kind of error did we make? Is that type 1 or type 2? What did we choose to do? We chose to reject the null. So if this was a mistake, that would be type 1 error, right? So if our decision to reject the null hypothesis is wrong, then that is a type 1 error. You want to take a short break? No? All right. Okay. I'm going to keep going. You can, if you want, you know, we're almost done. We got page 5, and then page 6, and then we'll be done. And this is like this practice final is actually longer than the real final. So if I'm getting through the practice final, talking everything through, all within, you know, less than 2 hours, you guys should be golden for the actual final, right? Of course, I know what I'm doing, but. All right, let's. We'll just. we're just going to quick fly through these, okay? In a certain city, a study was conducted to see if the police department had a different proportion of minority employees than the fire department. Researchers randomly selected 200 employees from both the police and fire departments, took note of whether the employee was a minority or not. 200 random police department employees, 80 of them were minorities. 200 random fire department employees, 50 of them were minorities. Okay. Is this evidence that the two departments have different proportions of minorities? Do we have, let's see, this is 34 to 39. Okay, 2 samples, right? Means or proportions? Proportions, we're looking at the proportions of minorities, and we're doing a hypothesis test. Okay, so 34, write the appropriate hypotheses. So here we're dealing with 2 samples, 2 populations, proportions. What's our null hypothesis going to be? Proportions, we say P, and I've got 2 of them, so I'm going to have P1 equal P2, and the alternative will be what? We're just asking, are they different? So we're going to say different, okay? So null hypothesis, we know, always has an equal sign. That will help you eliminate some wrong answer choices right off the bat. If the null doesn't have an equal sign, you know it's not going to be right. Okay, for the hypothesis test, what's the value of p hat? Okay, so let's go through. We got 200 and 200, so this is going to be n1 and n2. 80 is going to be x1, and 50 is x2. Okay, and so the p hat is x1 plus x2 all over n1 plus n2. So I'm going to do 80 plus 50 over 200 plus 200. So 80 plus 50 is 130. 200 plus 200 is 400. 130 divided by 400 is 0.325. .36, we got to get our test statistic. So this is going to be p hat 1 minus p hat 2 over the standard error. Standard error is given by our formula p hat times 1 minus p hat over 1 over n1 plus 1 over n2. I'm going to go ahead and, so I got 0.325 times 1 minus 0.325. 1 over n1 is 1 over 200 plus 1 over 200. Okay, so I have 0.325. I'm going to just say answer times 1 minus the answer times 1 over 200 plus 1. Oops, I messed something up here. Okay, I got to type like a peasant now. Okay, 1 minus 0.325 times 1 over 200 plus 1 over 200. Close parentheses, we hit equals there, and I hit the square root of the answer key. 0.046837. Okay. P1 hat minus P2 hat over the standard error. So P1 hat is going to be 80 over 200, and P2 hat is 50 over 200. 80 over 200 minus 50 over 200 divided by the standard error, which I have here. So I'm going to do parentheses 80 divided by 200 minus 50 divided by 200. Close off the parentheses, divide by the answer, 3.202.
Professor?
Yes.
Can you remind me, how did you get on the top 80 over 200 minus 50 divided by 200?
P hat 1, so P hat, so you know, maybe I did this a little too quickly. So P hat 1 is going to be 80 divided by 200. It's the proportion of minority employees in the police department. And P2 hat is going to be, you know, x2 over n2, 50 over 200. Okay, so I just kind of threw that in there. Okay, but yeah, maybe I should put that there. x1 over n1, which in our case is going to be 80 over 200. p2 hat, x2 over n2, 50 over 200. Okay, so I guess this is 0.40 and this is 0.25 if we wanted to. You know, it doesn't matter where you do the math, but so now we get a z-score of 3.2025, 256 technically, so that would round up. 37 says what's the p-value? So what I'm going to have to do is I'm going to have to take this and look it up in our z-table. So we look up z equal to 3.20 in our z-table. So we go to 3.20, and I get 0.9993. Okay, so the area to the left is equal to 0.9993. So my alternative says it's not equal, so I've got to double that, right? Now I know I can't double this, because if I double this, I'm going to get an answer bigger than 1. So what I have to do is I have to do 1 minus this first, and then I would double that. Okay? So I can't double this, because if I double it, I'll get an answer bigger than 1. So I'm going to do 1 minus this, and I get 0.0007, and now I double this. So my p-value is equal to 0.0007 times 2, and I get 0.0014. Is that okay? Okay, so for 38, you know, what is the conclusion we make? So based on our p-value is 0.0014, we're going to reject the null hypothesis. We have evidence that the proportion of minorities is different between the two departments. Proportion of minority employees is different. Okay. Yeah. Oh, it's not like that at every city, but this is what this shows. Okay. I'm sorry? Oh, 39. 39. So what is 39 says, what would a type 1 error be? So type 1 would be rejecting the null if the null was actually true. So what does it mean for the null to be true? It means the proportions are actually the same, but we have rejected that. So type 1 error would be the proportion of minorities is actually the same, but we believe it is different. Yes.
For number 38, how did you reject the null?
Okay, so my p-value is 0.0014. Okay, I don't think an alpha was specified in the problem. So if it's not specified, you assume that it's 0.05. And so my p-value would be smaller than 0.05. And anytime your alpha is, anytime your p-value is smaller than alpha, you reject the null hypothesis. Okay. Ready to keep going? Here we go. Oops. 40 through 44. Okay, potatoes are sold at the grocery store in 5-pound bags. You decide to weigh a random sample of 10 different bags. You find that the average weight of these bags is 5.2 pounds with a standard deviation of 0.3. Is this evidence that the bags at the grocery store have a mean weight different from 5 pounds? Okay. All right. How many samples do we have? One sample, and are we dealing with means or proportions? Means, right? And here it says we're doing a confidence interval. Okay, how many degrees of freedom do we have? N minus 1, so how many bags did we look at? We did 10. So our degrees of freedom, N minus 1, we're going to do 10 minus 1, 9 degrees of freedom. Okay, the value in the center of the interval, that's just going to be x bar, right? Confidence interval is going to be x bar plus or minus t star times the standard error, which is s over the square root of n. Okay, all of this, again, is in your study guide. So the center of our interval is x bar, which is, maybe we'll label these, 5.2, 0.3 is going to be my s, 10 is my n. 5.2, 42, standard error is s over the square root of n, so 0.3 over the square root of 10. I get 0.09486. Okay, so I'll just round off. 0.094, I'm going to just say 9 for 42. Okay, let's make the 95% confidence interval. Okay, so I've got 9 degrees of freedom, 95% confidence. So we're going to go to the reference table. 95% confidence, 9 degrees of freedom, 2.262. I think that's the second time we've seen that number today. Oh, I'm sorry. So this is t star. So our confidence interval will be x bar, 5.2 plus or minus 2.262 times 0.0949. Okay. So I'm going to multiply that by 2.262. And I get 5.2 plus or minus 0.2146. So on the high end, this gives me 5.4146, and on the low end, I think this gives me 4.9. Let's see. 5.2 minus the answer, 4.9854. Okay. So this is my resulting confidence interval. And then the question is, does the confidence interval, provide evidence that the grocery store has a mean weight different from 5 pounds? So we are looking to see if 5 is within our interval, right? So we say 5 is within our interval, so what does that mean?
We reject.
Okay, so that means we do not, there's no null hypothesis here because we're doing confidence intervals, okay? So we say we do not have evidence that the mean weight of bags of potatoes is different from 5 pounds. Okay, because 5 is a plausible value for our confidence interval. And 5 is a plausible value because it's within our confidence interval. Okay. It's not so bad, right? Okay, and then, all right, this is the last one of the math stuff. And then it's just easy stuff after that, or in my opinion. Okay. A fair die should land showing number 4 1/6 of the time. You roll a die 100 times and count how many times it lands as number 4. And it lands as the number 4 20 times. Is this evidence that the proportion it lands 4 is different from 1/6? Okay. So what is this? This is 45 through 49. Okay, how many samples do we have? We have 1 sample, and are we dealing with means or proportions? We're talking about which side the die should land on. Proportions, right? And it says we're doing a hypothesis test. Okay, what is the appropriate hypotheses? So one sample proportion, my null hypothesis will be what? Proportions, it's always going to have a p, right? And there's only one, so I don't need to label it p1 and p2. So p is equal to, according to this, it should be equal to what?
4.
Not 4, 1/6, right? It should land on the number 4 1/6 of the time. The alternative is that, is it different from 1/6? So we're going to have not equal to 1/6. What's the sample proportion? Sample proportion is that we rolled it 100 times and it landed 20 times. So p hat is going to be 20 out of 100, or 0.2. 47, standard deviation of our sampling distribution. This is just another fancy way of saying what is the standard error. Okay? So for the standard error hypothesis test, do I use p hat or p? P, okay? And if you're not sure, you can always go to the study guide and you say, oh, test statistic, standard error. And for one sample proportion, we can see it says p and not p hat, okay? So my standard error, I'm going to have p times 1 minus p over n. So I'm going to have the square root of 1/6 times 1 minus 1/6 over 100. So 1/6 times, parentheses, 1 minus 1/6, close parentheses, divided by 100. I'm going to take the square root of that. I get 0.03727. Okay, test statistic. Okay, is going to be z p hat minus p from the null hypothesis divided by our standard error. So I have 0.2 minus p from the null hypothesis is 1/6 divided by our standard error. I'm going to have parentheses, 0.2 minus 1/6, close parentheses, divided by the answer, my standard error right there. I get 0.8944. This is my test statistic. And 49, what conclusion do we make using alpha equal to 0.05? Okay, so what we have to do is we look up z equal to 0.89. Whoops. So looking at our reference tables, we look up z equal to 0.89, and I get 0.8133. So the area to the left is 0.8133. It says not equal to, so I'm going to have to do some doubling. If I double this, I'm going to get a number bigger than 1. So I'm going to do 1 minus 0.8133 first. I have 0.1867. Then I multiply that by 2. And I get 0.3734. So this is my p-value. And if I compare that to my alpha, which is 0.05, what happens? We do not reject the null hypothesis. Seems good?
So our p-value is greater than the...
Yeah, your p-value is greater than alpha. So that means do not reject the null. All right, let's, okay, let's take a look at these.
Professor,
Yes.
You mentioned that there's going to be 20% of old material, right?
Yeah, something like that.
So is this the 20%?
Yeah, this is the 20% of old material. Okay. All right. Oh, these were on your practice quiz, but okay.
The 53?
50, 50, 51, 52. So these are the sampling questions. Okay, Major League Baseball, or MLB, wishes to conduct a survey of its players. Instead of trying to create a list of all players from all their teams, which they actually do have, MLB decides to randomly select 4 of their 30 baseball teams, and they're going to survey all of the players on the 4 selected teams. So what kind of sampling is this?
Cluster.
Cluster sampling, right? The teams are clusters. They're going to just randomly select the teams. Okay, a company wants to survey its employees. They take a master list of everyone in the company and randomly selects 100 of them for the survey. What's that? That's simple random sampling. Master list of everybody. Toll bridge wants to survey drivers who use the bridge. They decide to stop every 10th car.
Systematic?
Systematic sampling. Okay? Simple enough, right? Yes. Okay, and then of course these are a little bit different from what you'll see on the final, but these go over kind of just older stuff from before the midterm that there's no math involved, but you know, you should note this. Okay, so bar chart, we use that for what kind of data? Numeric or categorical? Bar chart. Bar charts for categorical. What else do we use for categorical data?
Pie charts?
Pie charts, frequency tables, okay? What about numeric data? What would we use to display numeric data? Histograms? What else? Box plots? Dot plots? Okay, if we have 2 numeric variables, then what do we use? Two numeric variables, we use a scatter plot. Right? Kind of sounding familiar? Okay. All right. Two-way tables is for what? 2 categorical variables, right? Okay.
What do two-way tables look like?
Two-way tables. What does a two-way table look like? It looks like, I don't know, male, female, Democrat, Republican, or something. I don't know, I'm just making stuff up here, okay? That's what a two-way table looks like. Okay, in a normal model, approximately what percentage or what proportion of the data is within 2 standard deviations of the mean? 95, right? How much is within 1?
68.
68? What about 3?
99.7.
99.7, there you go. Okay, you guys remember this? No? Okay. It's just kind of, that's the empirical rule. So maybe you want to write that down. Look.
Can you write that down?
Okay, all right, we'll do.
What?
Empirical rule, all right? So things that are approximately normal. What does it mean to be approximately normal? What kind of shape do we have? Unimodal, and what else? And symmetric, right? So unimodal and symmetric means like we're this, okay? So within 1 standard deviation, 68% of data. Within 2 standard deviations, what do we have? 95% of data, about. Okay, these are all approximations. And within 3 standard deviations, almost 100, but we're going to just say 99.7% of the data. Okay, almost 100% is within 3 standard deviations when you've got a distribution looking like this. Okay, but of course not everything looks like this. What are some things that look like this? Examples of this: height, human height, intelligence, other stuff. Okay? Mountains, yeah. Yeah, not exactly, okay?
Do we need to know that height, weight, intelligence stuff?
Not weight. Weight is not normally distributed, okay? And because of modern technology and stuff, weight looks like that now, okay? We have people out here. Meaning, this is what do we call this? Skewed what?
Right.
Right skewed, right? Okay, and what does it mean to be skewed right?
With the kebab on the left.
Huh? You put the shish kebab on the right, okay. And regarding but numerically, what does it mean?
Has a tail.
yeah, that's true. Okay, no, it means you can be. We have values much higher than what we consider the normal or average. Okay,
Oh.
but do we have any the opposite direction? Down here? No one's out here. Okay, so when we talk about human weight, average, whatever. Let's say the average person weighs 160 pounds. I have no idea. Okay. Are there people who weigh 300 pounds? Yes, okay, we don't have a lot, but there are people who weigh 300 pounds. 300 pounds is like 140 pounds over the average of 160, okay? Do we have anybody weighing 140 pounds less than 160? So 160 minus 140 is 20 pounds. Do we have any adults weighing 20 pounds?
Benjamin Button.
Yeah, no. Okay. We shouldn't. Okay. Maybe because of genetic conditions, but so that's what it means to be right skewed. We have numbers out here. Same thing with the income. Income is right skewed. Average income is probably like 50,000. There's people that make $1 million a year or more. Okay, that's 950,000 more than average. What is 950,000 less than average? That's making negative 900,000 a year. That's
You could do that.
Huh? Not in terms of a legal wage, okay? It's okay. Yeah, you might there might be people coming after you, but in terms of a legal wage of getting paid, you can't get paid negative 950,000. That's every minute you work, you owe me more money. Okay, that's how bad of a job you're doing. The intercept in linear regression would be our predicted value when x has what, okay? Intercept in linear regression is our predicted value for y when x is 0, okay? What about the slope? It's how much we predict y to change when we add 1 to x. Okay? If the probability of A and B happening together is 0, then that means A and B are mutually exclusive. There you go. Okay. What's true if A and B are independent? Yeah, if they're independent, they're not mutually exclusive. That's true. If they're independent, the probability of A given B is equal to the probability of just A happening by itself, right? It doesn't matter whether B happened or didn't happen. Probability of A happening is probability of A happening, whether B happened or not. Okay, for a quantitative variable or numeric variable, if there's only one peak, what do we call that? Unimodal. What measure of center is not influenced by outliers? The median, right? Okay, so it's stuff like this, right? It seems like maybe you have forgotten a lot of this stuff. But I don't know. I guess you can kind of flip back through some of this. You know what? Oh, let me. Okay, so I'm going to stop the recording here.